Somewhere beneath your feet right now, in cities across every continent, machines the size of apartment buildings are eating through solid rock. They run 24 hours a day, 7 days a week, for years at a time. They never stop. They never come back to the surface. And by the time they finish, they have bored a perfectly circular tunnel, installed its concrete lining, and left behind infrastructure that will be in use for a century. The tunnel boring machine is one of the most complex pieces of engineering ever built. And almost everything about how it actually works is different from what most people imagine. It does not drill, it does not blast, it does not cut in the way a blade cuts through material. What happens at the face of a tunnel boring machine is something more precise and in some ways more violent than any of those things. The front end of a tunnel boring machine is a rotating disc called the cutterhead. On a large machine, and large means 15 to 17 meters in diameter, roughly the height of a 5-story building, this disc can weigh several hundred tons on its own. It is studded with disc cutters, hardened steel wheels arranged in a pattern of concentric rings across the face, each one mounted in a steel housing and designed to rotate freely as the cutterhead turns. The entire cutterhead presses against the rock face with enormous force, typically between 5,000 and 20,000 tons of thrust, depending on the machine and the geology. Then it rotates, typically between 1 and 5 revolutions per minute. Slow by any intuitive standard, but at that scale, the outer edge of the cutterhead is moving at a significant speed, and the disc cutters are pressing against the rock with loads of up to 30 tons per cutter. Here is the critical thing to understand about what actually happens at the rock face. The disc cutters do not cut the rock, they crush it. As a disc cutter rolls across the rock surface under extreme load, it creates a zone of intense compressive stress directly beneath the contact point. Rock is strong in compression, you can press on it, but it is weak in tension. The compressive stress from the cutter generates tensile cracks that propagate outward from the contact zone, connecting to adjacent cracks from neighboring cutters. Chips of rock fracture off between the cutter tracks and fall away. The machine is not removing rock continuously, the way a blade removes material. It is inducing fractures and collecting the chips that result. The disc cutters are carefully spaced so that the crack patterns from adjacent cutters overlap precisely, maximizing the size of each chip and minimizing the energy required to break the rock. Too close together and the cutters create redundant fractures. Too far apart and the rock between them doesn't break cleanly. Getting this spacing right for a specific rock type is one of the primary engineering challenges in designing a tunnel boring machine for a given project. Different rock types, for example granite, sandstone, limestone, and clay, fracture differently under load, and the cutterhead geometry has to be matched to the geology. While the cutterhead is breaking rock at the front, an entirely separate system is managing the material it produces. The broken rock, called muck in tunnel engineering, falls through openings in the cutterhead face into a collection chamber. Rotating scoops built into the inner surface of the cutterhead pick up the muck as the head turns and deposit it onto a conveyor belt running through the center of the machine. That conveyor carries the muck backward through the machine and into a trailing system that can stretch hundreds of meters behind the boring head. A connected chain of gantries carrying power cables, ventilation ducting, water lines, concrete segment supply chains, and all the other systems the machine needs to operate. At the far end, the muck is either transferred to rail cars, trucks, or a secondary conveyor that carries it back to the surface. On a large project, this material removal operation runs continuously and in parallel with boring. The machine cannot stop to clear muck. It produces muck at a rate determined by its advanced speed, and the removal system has to keep pace at all times. In some geological conditions, particularly soft ground or areas where the tunnel passes beneath groundwater, the muck removal becomes significantly more complex. Slurry tunnel boring machines use pressurized bentonite slurry to fill the chamber ahead of the cutterhead, providing face support to prevent collapse and mixing with the excavated material to create a pumpable slurry that is piped back to the surface for separation and recycling. The engineering required to balance face pressure, slurry density, and advance rate in variable geology is some of the most demanding in the entire field of underground construction. At the same time the cutterhead is boring and the muck removal system is running, a third operation is happening directly behind the machine. The tunnel lining is being installed. Precast concrete segments, typically 6 or 7 per ring, and each one weighing several tons, are transported from the surface through the trailing gantry system and fed into the machine. A robotic arm called an erector picks up each segment and positions it with precision, building the ring immediately behind the machine's cylindrical steel shield. When the ring is complete, hydraulic rams push against it to advance the machine forward for the next cycle. The shield, the outer steel cylinder that encloses the machine's mechanical systems, provides temporary support to the tunnel walls immediately behind the cutterhead before the concrete lining is in place. As the machine advances, the shield moves with it, and the completed concrete ring is exposed to the ground. Grout is injected into the annular gap between the ring and the surrounding ground, locking it in place and preventing settlement. The entire sequence, bore, collect muck, install ring and advance, is continuous. At any given moment, the machine is simultaneously cutting rock at the front, removing material in the middle, and building a finished tunnel at the back. A large TBM on a favorable geology can advance 30 meters or more in a single day. On exceptionally hard or abrasive rock, progress can slow to a few meters per day. The single most critical and vulnerable component on a tunnel boring machine is one that most people have never thought about: the main bearing. The cutterhead, weighing hundreds of tons, pressing against rock with thousands of tons of thrust, rotating continuously, is mounted on a single large diameter bearing. This bearing transmits all of the thrust and rotational forces between the cutterhead and the machine body. It is a masterpiece of precision engineering. It is also completely inaccessible once the machine is underground. If the main bearing fails mid-tunnel, the project does not stop temporarily. It faces a potentially catastrophic problem. The machine cannot be brought back to the surface. Engineers either have to excavate a rescue shaft from above, which is enormously expensive and only possible at certain depths, or construct a bypass adit, a small manually bored side tunnel to allow workers to access and replace the bearing underground. The most famous example of this kind of failure occurred on the Seattle Highway 99 tunnel project, which used a machine called Bertha. At the time, it was the largest tunnel boring machine ever built, measuring 17.5 meters in diameter. In December 2013, 14 months into the project, Bertha stopped advancing. The cutterhead had hit a steel pipe left underground by a previous survey operation. The impact damaged the main bearing seal. Contaminated lubrication accelerated bearing wear, and the machine ground to a halt after advancing only a small fraction of the total tunnel length. The repair required mining a 38-meter deep rescue shaft, lowering replacement parts weighing hundreds of tons into the pit, and rebuilding significant portions of the machine underground. The project was delayed by more than 2 years. The final cost was hundreds of millions of dollars over the original estimate. Bertha eventually completed the tunnel in 2017. But the episode became one of the most studied case studies in tunneling history, a demonstration of what happens when the most critical component of a machine you cannot retrieve fails in the middle of an operation that has no pause button. There is a maintenance operation that happens regularly on every tunnel boring machine that most people find genuinely surprising the first time they hear about it. The disc cutters wear down. Rock is extremely abrasive, and even hardened steel cutters have a finite life, sometimes as little as a few hundred meters in highly abrasive granite before they need replacement. On a project that bores several kilometers of tunnel, cutters may be replaced dozens or hundreds of times. On most machines, this requires workers to enter the cutting chamber, the pressurized space immediately behind the cutter head face, to physically remove worn cutters and install new ones. In soft ground or high water table conditions, this chamber must be pressurized above atmospheric pressure to prevent the face from collapsing. Workers enter through an airlock and perform the replacement in conditions similar to those experienced by deep-sea divers. At extreme pressures, in deep underwater tunnels, this requires saturation intervention, where workers spend days in a pressurized environment and decompress slowly over multiple days to avoid the same pressure-related injuries that affect divers. It is one of the most physically demanding and technically specialized jobs in any industry. The cutter change operation is planned carefully into the project schedule. Machines are designed with as much access as possible to the cutting face, and some modern designs allow certain cutters to be changed from the atmospheric side of the cutter head without pressurized intervention. But in difficult conditions, there is no alternative to sending people into the pressurized face to do the work by hand. In 1994, 11 tunnel boring machines converged on the same point beneath the English Channel from two directions simultaneously, 6 from the French side and 5 from the English side, and the two halves of the Channel tunnel met with a horizontal alignment error of less than 5 centimeters over a distance of more than 20 kilometers bored through rock. 5 centimeters, 20 kilometers, underground, without GPS. The navigation systems used laser theodolites and gyroscopic instruments to track the machine's position relative to a known reference point. Course corrections were applied continuously through adjustments to the hydraulic rams that steer the machine by applying differential thrust around the ring. The geometry of every concrete segment and the precision of every ring installation was calculated and monitored throughout the bore. The accuracy achieved on the Channel Tunnel is still used as a benchmark for modern projects. It demonstrated that a tunnel boring machine is not simply a piece of heavy equipment. It is a precision instrument operating in conditions where the consequences of deviation compound over kilometers and cannot easily be corrected. The machines currently operating beneath cities around the world are the direct descendants of a concept that engineers first proved in the 1950s. From the disc cutter to the rotating cutter head and the simultaneous lining installation, the fundamental architecture has remained consistent across 7 decades of refinement. What has changed is scale, precision, and the ability to operate in geological conditions that would have stopped earlier machines entirely. Modern slurry machines bore through waterlogged sand beneath major rivers. Mixed ground machines transition between solid rock and soft clay within a single drive. Crossover machines can reconfigure their support systems mid-tunnel to handle changing conditions. Each project that pushes the envelope becomes the reference case for the next one. Every failure, every stuck machine, every bearing replacement, every flooded chamber generates knowledge that is absorbed into the next generation of design. Somewhere beneath your feet right now, one of these machines is advancing. It moves a few meters per hour, around the clock, pressing disc cutters against rock and collecting what fractures off, building the tunnel behind it as it goes. By the time you next walk over that ground, the machine will be kilometers further on, and the finished tunnel it left behind will be in use long after every person involved in building it is gone.